Imagine a highly structured, rigid, and traditional system suddenly hit by a massive, chaotic flood of new information. Relying on a single, monolithic database to run an entire enterprise application is an outdated practice. Historically, applications dealt with highly predictable data. A university, for example, tracks thousands of students, courses, and professors in neat, interconnected tables. But modern applications face a different reality: massive, real-time streams of unstructured data, from social media feeds to global telemetry. When that sheer volume of data exceeds the physical limitations of a single server, the challenge becomes maintaining system speed and availability. Elevating from a standard programmer to a data engineer requires mastering this architectural divergence, knowing exactly how to bridge traditional SQL and modern NoSQL systems. Understanding exactly when to deploy a relational database versus a non-relational solution is the definitive hallmark of a mature software engineer. Let's establish the baseline. SQL, or Structured Query Language, is the standard programming language designed specifically to extract and manage data within a relational database management system, or RDBMS. In our university example, storing everything in one massive spreadsheet risks data corruption. The relational model solves this by breaking information down into distinct, highly organized tables, one for students, one for courses, that relate directly to one another. This table maps out how SQL handles persistent storage through the four fundamental CRUD operations. You use insert to create a record, select to read it, update to modify it, and delete to remove it entirely. Built on relational algebra, SQL uses these operations to perform complex relational math. It can filter rows with strict criteria, aggregate sums, and stitch data together from multiple tables on the fly, using the join command. SQL is highly effective for performing complex analytical tasks directly where the data lives. However, at massive scale, this requirement for rigid, predetermined organization becomes a severe performance bottleneck. This comparison table illustrates the structural differences between SQL and NoSQL. Looking directly at the structure and schema row, we see a clear divide. SQL requires a schema on write. Blueprints must be designed before a single piece of data is saved. NoSQL operates on a schema on read philosophy. It is flexible, allowing you to insert data in dynamic formats, like JSON, without a pre-existing blueprint. When a SQL database needs more power, it scales vertically, migrating to larger, expensive servers until hitting a hard physical limit. NoSQL circumvents this ceiling by scaling horizontally, linking together cheap commodity servers into a sprawling cluster. By shifting to horizontal clusters, engineers bypassed the physical hardware limits of big data. This specific architectural choice is exactly what makes NoSQL absolutely necessary for modern applications dealing with high-velocity, massive-scale data streams. Returning to the matrix, SQL relies on ACID, atomicity, consistency, isolation, and durability, guaranteeing strict transactions. If an operation fails, it rolls back. Absolute precision required for financial processing. NoSQL, conversely, operates on the base theorem: basically available, soft state, and eventual consistency. Base intentionally sacrifices immediate, rigid consistency across the entire network. Instead, it prioritizes keeping the system available and processing queries instantly, ensuring eventual data synchronization. Engineers do not pick between ACID and base based on personal preference. They calculate tolerance for minor synchronization delays against the strict requirement for exact mathematical precision. This document outlines the NoSQL ecosystem, divided into 4 architectural branches. The first 2 are key value and document stores. Key value handles rapid caching, while document stores manage semi-structured formats, ideal for e-commerce catalogs. The final 2 are wide column and graph databases. Wide column stores handle extreme, write-heavy telemetry data. Graph databases treat data relationships as equally important as the data itself, crucial for recommendation engines and fraud detection. This brings us to polyglot persistence. Modern enterprise architectures rely on multiple distinct database technologies simultaneously. As shown, an application might pull its product catalog from a NoSQL document store, while securely routing checkout data to an ACID-compliant SQL node. SQL and NoSQL are collaborators required to build a complete system, not purely competitors. Mature systems actively integrate the specific strengths of both ecosystems. Storing data efficiently across a polyglot architecture is just the prerequisite. Extracting strategic value from that storage is the domain of advanced Level 3 data analytics. This text highlights advanced computational concepts. The first is distributed computing, enabling teams to process terabytes of data by breaking free from single machine constraints. Next is the analytical shift from establishing simple correlation to proving actual causality, relying on frameworks like difference in differences. Engineers also apply natural language processing, or NLP, to extract structured, usable insights directly from the messy, unstructured text logs resting in NoSQL databases. Modern databases function as the raw fuel for these computational engines. They bridge the operational gap between simply recording historical events and predicting future outcomes. To maintain these complex systems, teams rely on the operational principles of analytics engineering and data ops. These disciplines treat data pipelines as modular products. This pipeline diagram illustrates the flow, pulling raw data from diverse SQL and NoSQL nodes, pushing it through a central, version-controlled transformation block, and delivering it out to a clean analytics dashboard. Rigorous automation is exactly what makes managing the extreme complexity of combined storage and predictive models possible. By mastering polyglot architectures and building distributed, automated pipelines, trainees cross the threshold. They move beyond standard application programming and enter the precise discipline of enterprise data engineering.